Tarber for Precalculus. In this video, we're going to be talking about continuity and end behavior. The icons for this video, I can describe the three types of discontinuity. I can find the limit of a function using a table. I can use a limit table to determine the continuity of a function at an x value. I can use a table to approximate the zeros of a function, and I can use a limit as x goes to a positive or negative infinity to describe the end behavior of a function. Our outline for this video, we're going to talk about what continuity is for a function. We're going to take a look at the different types of discontinuity. Then we'll talk about what a limit is and how to use limits to determine continuity at a point. We're going to talk about the intermediate value theorem. We're going to look at using a table to approximate a zero of a function. And finally, we'll talk about end behavior. So let's talk about continuity first. A continuous function has no breaks in the graph. So one of the best ways to determine if a function is continuous or not is to look at its graph and see if there are any breaks. I always like to say that you can draw its graph without lifting your pencil. So if you can start the graph on the left, draw the curve, get all the way to the right, and never have to pick up your pencil, then that function is continuous. Now, if a function or a graph is not continuous, there's only three types of discontinuity that we need to worry about. There's what's referred to as an infinite discontinuity, a jump discontinuity, and what's referred to as a removable or a whole discontinuity. So let's take a look at what an infinite discontinuity is. So here's a function drawn out on my TI Inspire again, and it has an infinite discontinuity at x equals 2. This area right here, I would have to pick up my pencil, move to a different part of the graph, and then start drawing again. So it's not continuous at x equals 2. And actually what we've really got right here is a vertical asymptote. So these vertical asymptotes create discontinuities, and because the graph is going down to negative infinity on the left and it's going up to positive infinity on the right, that's why we call it an infinite discontinuity. These two pieces of the graph are literally infinity away from each other. We can also have a vertical asymptote where both sides of the curve are going up to infinity, or maybe they're both going down to negative infinity. It's still a discontinuity. Those two pieces of the graph don't ever touch. We have to pick up our pencil, jump over that asymptote, and then start drawing again. Now here's an example of a jump discontinuity. Right here again at x equals 2, I would have to pick up my pencil, move to a different part of the graph, and start drawing again. So we have a discontinuity, but it's just a jump discontinuity. This is usually coming from a piecewise function where we have a different rule to the left of a number, a different rule to the right of a number, and they just don't meet in the middle. Our last type of discontinuity is what's referred to as a removable or a whole discontinuity. We have a nice linear relationship here, but there's a hole right at x equals 2. Now the reason we call it a removable discontinuity is if I could go ahead and just define a single point, in this case the point 2, 4, it removes that discontinuity. So it's just a single point that's missing. It's not a region of numbers. It's just a single point missing out of the graph. So it's just a hole in this line. Now let's talk about limits. Okay? Taking the limit is a process where we take a look at the behavior of a function around really super close to a certain x value. One thing that I always tell my students is if I'm finding the limit of a function at x equals 2, I never ever get to actually plug 2 into the function. I'm always plugging numbers super duper close to 2 into the function. I might be plugging in 1.99, 1.999, 1.999999, you get the idea. And I'll even plug in numbers on the other side, 2.001, 2.00001. Numbers that are really close to 2 because I'm trying to look at the behavior. but I never actually plug in 2 itself. Now, the best way to find a limit is with a table. So I've laid out a table here where I've got x values very, very close to 2 on both sides of 2. I've got numbers that are just a little bit smaller. I've got numbers that are just a little bit bigger. And I've plugged them into some function, and I'm looking at what is the function doing really close to 2. Now, if things agree, these numbers seem to be going in a progression somewhere. These numbers seem to be going somewhere. If they agree, then we can say that the limit exists. So do these two sides seem to agree? Do they seem to be pointing to the same value? And the answer is yeah, they both seem to be leading us to 5 at x equals 2. So we say the limit as x approaches 2 of the function f of x is equal to 5. Both sides of the table were leading us towards a 5 right there at 2. Now, in order to use limits to determine continuity, what we need to do is find the limit at that point that we're checking. So I want to find the limit at some x value. We do that with the table. I want to find the value of the function at that point. I want to be able to plug in to the function. Now maybe it's a piecewise function. I've got to really pay attention to which rule I'm going to use. And if they are the same, that is, if I take the limit coming together from the left and from the right, and when I plug in that value, if I get the exact same answer, then the function is continuous at that point, and we call it a point of continuity. So basically what we have here at the bottom is the limit as x approaches a. Maybe that a value is 2, as we saw earlier. So the limit as x approaches a of f of x. If that is actually equal to what we get when we plug in a, then the function is continuous. Now let's talk a little bit about the intermediate value theorem. Here it is in all of its glory, word-wise. If f of x is continuous function and a is less than b, so a is going to end up being an x value, b is an x value, and a is smaller than b, and c is a value between a and b, so it's bigger than a but smaller than b, then f of c is between f of a and f of b. That means that the y value at c is between the y values for a and b. So what we're talking about here I've got some function drawn out in my graph. I've got a, it looks to be a is about 0, and I've got b over there at, looks like it's about 6, but a is less than b. This is a continuous function that I can draw from the left side of my graph to the right side of my graph without picking up my pencil. If I choose any value in between a and b, if I choose any value between a and b, its y value has to be between f of a and f of c. If I can draw smoothly from a to b on my graph, then that has to be true in the y direction as well. I have to include every single y value between f of a and f of b. Now that doesn't sound like a real big idea, but it's actually a really big idea when we're trying to find zeros of a function, which is actually what we need to talk about next. Using a table to approximate a zero. So this table I made with the function f of x equals x cubed minus 4x plus 2, and I started my table at -4, I ended it at +4, and I'm only using integers. I'm just trying to approximate where a zero is. Now if you take a look at the y values, what we're looking for is 0 in the y values. Now I don't actually have a 0 in the y values, but I'm trying to guess where a 0 might be. Well, it turns out that all polynomial functions are continuous. I have a polynomial function. It is continuous. So my intermediate value theorem actually helps out here and says, hey, if I go from a negative y value to a positive y value, or vice versa, at some point in there I have to go through 0. So the intermediate value theorem is actually pretty useful, because I go from a negative y value to a positive y value right here between -3 and -2. I go from a positive y value to a negative y value between 0 and 1, so I know that I've got a 0. I know that I go through the x-axis there, and there's even one more right next to it. I know that there's another 0 between x equals 1 and x equals 2. So by making a table like this, I can approximate my zeros, and I can say, okay, I've got one between -3 and -2, probably closer to -2. I've got one between 0 and 1. I've got one between 1 and 2. So if we take a look at this again, just to put kind of a wrinkle on here, I have another continuous function. It's a polynomial function. I'm going from -3 to 3. Now, there's a big thing here. I don't actually have a positive in one box and a negative in the next. But take a look right in the middle at -1 and 0. They have the same y value. Now, what may be happening, especially with a y value that small, my graph may dip down and hit 0 in between these two. So I may have a 0 to this function, or I may actually have more than one. There's actually 2 in this function. I may have more than one 0 in between x equals -1 and x equals 0. We can always graph this and take a look at this to see, do we have a 0 between -1 and 0? Now let's talk a little bit about end behavior. An end behavior of function literally is trying to describe what's happening to our graph as it goes to the extreme left, that is as x approaches -infinity, and as we go to the extreme right, as x goes to a positive infinity. We basically only have 3 options. I don't know why there isn't an S on that options, but whatever. It could be going to a positive infinity, so the graph could be going up. It could be going to a negative infinity, that means that the graph is going to be going down. Or it could be going to some number, and yes, that number can be 0, and that's what we explored in Algebra 2 when we were looking at horizontal asymptotes. A horizontal asymptote is end behavior. It's approaching some number as it goes to the extreme left or the extreme right. Now, there is a super secret fourth option that we're not really going to be talking about today called an oblique asymptote, but we'll save that for later. So, here is a nice function. Seems to be a quadratic maybe. It's definitely an even function. It's got a even power at least. I shouldn't say that it's an even function. It's got an even power. So this end behavior, the limit, so we're using that limit notation again, as x approaches infinity. That is, as x goes to the extreme right, this function goes up. So this function approaches positive infinity. And the same thing is going on the left side. The limit as x approaches negative infinity. It's going up. Our function is going to a positive infinity. We might have one side going up and one side going down. In this case, as we go to the right, as the limit as x approaches infinity, the function is equal to an infinity. The limit as x approaches negative infinity, it's going down, so the function is approaching negative infinity. So when we say that they're approaching infinities, they don't have to both be going up, they don't have to both be going down. They can be going in opposite directions with end behavior. And here's our last type of end behavior. This one's going to be a horizontal asymptote. And the question is, where is that horizontal asymptote? You might need to graph this function farther out, but this function is going to 0 as it goes to the right, and it's going to 0 as it goes to the left. So, that's it for this video. I'll see you in class, and I'll see you online.